Hello, my name is Yongu Park, and I'll be presenting our work on super resolution in vivo human MR imaging today. High resolution MR imaging with resolution of 100 micrometer per voxel or above could significantly enhance visualization of brain anatomy, which could have clinical uses in detecting microlesions in diseases such as epilepsy or multiple sclerosis. It could also help understand human brain anatomy, particularly in small and complex regions such as the cerebellum. However, any increases in spatial resolution comes at a cost to signal-to-noise ratio, and that is because MR signal comes from protons within a voxel, and having a higher resolution image means signal will be coming from a smaller volume. One strategy to alleviate the issue is to acquire image at a higher magnetic field scanners, such as 7 Tesla ultra-high field scanners. Theoretical availability of protons is directly proportional to the field strength, so ultra-high field will have better SNR. However, this gain alone will be insufficient to counter the decreased voxel volume due to increased spatial resolution. What complicates the issue further is that it will increase the scan time needed for imaging due to longer readout length and sometimes for signal averaging to counter the SNR loss. Also, those familiar with imaging at ultra-high field knows that safety limitations related to SAR and the changes in the tissue T1 and T2 coefficients could further complicate the high-res imaging acquisitions. So to tackle these issues, I have looked at how other imaging modalities generate higher resolution images. In digital cameras, such as DSLR, pixel shift technology has been used to generate higher resolution image from lower resolution sensor. This technique, also known as super resolution, involves acquiring multiple images with physical displacements of the image sensor. And once multiple images are collected, the image processor in the camera combines the image to generate the final high resolution image. I'll use the following figure with orange balls to explain the super resolution. Here, orange balls represent individual pixels in an image, and each pixel represents a probability density function. Another image is acquired with physical shift, and the shifted image has different probability density pattern. Now, we use these information from the original pixel and the shifted pixel to generate the pixel values between the original pixels, as highlighted by the darker shade of orange here. And once you fill those information, you end up with higher resolution image. Note that there are examples of super resolution adopted for MR imaging. However, it's mostly focused on scan time reduction for using compressed sensing. For this work, we're trying to generate a very high resolution images with super resolution using readily available hardware and software packages for high reproducibility. To test our method, we acquired MR images using commercial hardware with Siemens 7 Tesla Terra scanner and a single channel commercial transmit coil from Nova Medical. We slightly modified the imaging pulse sequence to acquire more than 1,024 sample points. And we acquired with sub-pixel shift controlled using auto-align. And we used publicly available super resolution code to perform super resolution and combine multiple MR images with sub-pixel shifts. For those who are not familiar, auto-align is a feature in Siemens scanners that automates positioning of image acquisition location and angulation. And one could override the image center position with offset in the protocol editor with sub-pixel offset. And auto-align will compute the shifted position in the subject space automatically. Three different validations were performed. First, we wanted to compare the high-resolution image against the comparable super-resolution image. We also wanted to test if we could acquire a very high-resolution image, close to 100 micrometer resolution in different image contrasts. And finally, we wanted to see if super-resolution could be used to acquire 3D volume with isotropic voxels. Comparing higher resolution to super resolution, one can see slightly sharper edges in the high resolution. Um, However, the high resolution image is grainier, indicating lower signal to noise ratio, and there's also worse tissue contrast with white and gray matter separation more profound in SR. It also appears to be affected by motion artifacts, which may be due to longer scan time of the high-resolution scan. Super resolution was used for various other contrast types, such as T1 and SWI. Here's an example of T2 weighted image. And the SWI image. Finally, a T1 image. Unfortunately, we had difficulties in acquiring a high-resolution T1 image close to 100 micrometer per pixel in resolution, and this is due to longer readout needed for a high resolution, and also SAR safety limit at ultra-high field made it really challenging to achieve short TR and short TE necessary for T1 weighting. Hence, we use 3D NP rate sequence with GRAPPA compressed sensing to acquire a 3D T1 volume at 0.6 millimeter isotropic resolution. And this, we acquired four of it to make it 0.3 by 0.3 by 0.6 resolution images. Finally, we show an example of creating a 3D volume with super resolution. So far, we've been acquiring high-resolution 2D images with slice thickness much greater than voxels width or height. So we could do a super resolution in the slice direction to create a 3D volume with isotropic voxel dimensions. This would be useful in applications such as imaging occipital cortex or cerebellum. So for this proof of concept demonstration, we acquired 4 sets of coronal images, each about 11 minutes for a total of 44 minutes. Super resolution is then performed to generate a 3D volume with 0.3 millimeter cubic voxel volume. Resulting axial and sagittal slices are shown here, and the corresponding 3D volume render is shown. Note that occipital cortex looks good, though a weak signal around lower part of the cerebellum meant cerebellum portion still needs some additional work. So to summarize, we have shown that the super resolution yields comparable image quality to high resolution with several pros and cons. And it can be easily implemented using available technologies such as commercial hardware and software such as AutoLine. We have also shown that SR works on different types of MR image contrasts. And finally, it can be expanded to acquire a very high resolution 3D volume data. I would like to close this presentation by mentioning other potential venue of improvements for MR images, inspired by advances in camera and other image processing domain. First, machine learning-based super resolution has basically taken over the image processing field, and we can certainly use similar machine learning technique to enhance the MRI resolution. Second is image fusion is another popular image processing method that is commonly used by phone cameras nowadays. And we could think about further image enhancements by acquiring images with not just subpixel shifts, but also with different contrasts. I'd like to acknowledge the collaborators and funding sources. Thank you for listening.